We're going to be putting chapter 4 and chapter 5 together in this next chapter, just because the information in them just really goes well together, and we're also not going to go into the information as much in depth as what your book is, because you're going to be doing so much of that in chemistry class, and we aren't going to go into the depth just because I think it's a little bit much for a physical science class. We're going to be talking the next 2 chapters a whole lot about the periodic table. And so you need to get in the habit of, whenever you watch a video from me or whenever you do your homework, whenever you take your test, you'll need to make sure that you have your copy of the periodic table in front of you. And whether you are using the one in your book, which I said I believe is on the inside back cover, but I know it's in the chapter where we had used it before, or whether you have made a copy of it and you have a separate copy and you've got that next to you, you're definitely going to be using the periodic table all the time. I did draw a copy of the periodic table on the board just because I knew I wasn't going to be able to hold it up and point to everything. So we want to start by pointing out that of all the elements that are represented on the periodic table, and I did mention this when we were in chapter 3, that when you write the symbol for an element, if you write it with just one letter, that letter has to be capital. And if the symbol for the element has 2 letters, the first letter needs to be capital and the second letter needs to be lowercase. Now, I know there are some people, and I don't know if any of you have gotten into this habit, I know there are some people who like to write everything in capital letters. I've also seen there are some people that seem to write everything in lowercase letters, even their names. I've had some students who turn their work in and their first and last names aren't capitalized. They write them with a little letter. I've never quite understood that because that's not proper English. But if you're going to do chemistry, you have to write both capital letters and lowercase letters. And let me show you why. If you look at an element like cobalt, cobalt is a metal, and the symbol for that is a capital C and a lowercase o. But there's also, if I make a capital C and a capital O, this stands for an atom of carbon and an atom of oxygen. And this compound is called carbon monoxide. And carbon monoxide is poisonous. If you breathe in a whole lot of carbon monoxide, it will kill you, because what it does is it binds up the hemoglobin in your red blood cells so that they can't absorb the oxygen that they need, because it's easier for them to bind to the carbon monoxide instead. And so you actually are going to die if you breathe in a lot of carbon monoxide. So this is deadly. This is not. Another example is an element called hafnium, HF, capital H, little f. This also is a metal. So both of these are metals. This, however, if I write it with a capital H and a capital F, this means I have an atom of hydrogen and an atom of fluorine that are bonded together. This is called hydrofluoric acid, and it is an extremely caustic acid. Very, very dangerous. And so again, you've got 2 things that are very, very dangerous versus 2 things that are just metals, and they're very different from each other, and so you need to make sure that you write the letters different for each other as well. So you want to really watch that when you're writing, especially a lot of these elements that have 2 letters for them. Make sure the first one is capital and the second letter is lowercase. Now, we've talked before about how the periodic table is organized according to atomic number. And we said now I don't have all the atomic numbers and atomic masses on here too. That would have been a little too much to try to cram into my spaces. But if you have your periodic table in front of you, you can see that the atomic numbers, again, as we've talked about before, they increase as you read the table from left to right and from top to bottom. So hydrogen is atomic number 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, and so on. And you read it just like a book, left to right, top to bottom, and those atomic numbers will increase. Now, the other number in the box, again, we talked before, is the atomic mass. And it's kind of an average of all the different atoms that are in that particular element. Again, I won't go back all over that since we've talked about it before. But you'll notice if you look at your periodic table that those numbers increase as well, which would make sense. I mean, if you're going to increase the number of protons, the number of neutrons, then the atomic mass is going to go up as well. There are a couple of, actually there are 3 places on the periodic table where that is not true. If you look at argon and potassium. Now argon is right here on the periodic table and potassium is over here. And I'm going to actually get my periodic table out so I can actually see those numbers. The number for argon is 39.95 and the number for potassium is 39.10. So in that particular case, even though the atomic number went up from argon to potassium, the atomic mass actually went down. There are 2 other places on the periodic table where that happens, and I'm going to challenge you to find those 2 places. So see if you can find them, and then the answers are going to be in your assignment today in your daily lesson plan, so you can check and see if you're right there. We're going to talk now a little bit about the organization of the periodic table. They're organized into rows and columns, and it's really not true that somebody just decided to take a newspaper and cut it up and just hurl all the elements' names down there and just arrange them in some sort of random order. There really is a very good reason why they're organized the way that they are, besides just the fact that they go in order of increasing atomic number. Because the rows and the columns that they're in tell us a lot about each individual element. So first of all, we're going to talk about a family, and sometimes you'll also hear it called a group. The families and the groups go up and down, or in the columns on the periodic table. And if you look, you can see on your periodic table, as well as on the one I have up here, that there are 18 different columns, and they're numbered up here across the top. And those 18 columns are 18 different families or 18 different groups. And in a family or in a group, the elements that are in there are going to have very similar chemical properties to them. And remember that we said a chemical property has to do with how it reacts with something else. So anything that's in the same column is going to react similarly to anything else that is in that same column. And the reason that they have similar chemical properties is because the number of valence electrons they have is the same. Forgot to put the word number in there. Let's go back and fix that. Because the number of valence electrons is the same. Now, what is a valence electron? Well, you already know that the protons and the neutrons are together in the nucleus, and the electrons are around the outside. And you can think of it kind of like the shell, like different layers of an onion. And you can put a small number of electrons in the first layer, it's 2. The second layer holds 8. The second layer, or the third layer, holds 18. The next layer holds 32, and it keeps going, gets bigger and bigger the more layers that you add. So the valence electrons is the number of electrons in the outermost shell of electrons. Okay, so let's get that up here. Valence electrons is the electrons in the outermost shell, you'll hear it called that, or the outermost energy level, because the higher or the further out the shell is, the more energy those electrons have. Okay, so the number of electrons that energy level holds, if I go down a column, every element in that column has the same number of electrons in its outer shell. So, for example, hydrogen has 1 electron, helium has 2 electrons, and there are only 2 electrons that fit in the first energy level. And so Then if I'm going to add a third electron, I have to add a second energy level, a second layer to my onion. That second layer holds 8. So I've got 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to have 8 electrons in that second energy level. But what that means is that over here for your hydrogen and for your lithium, both of them are just going to have 1 electron in the outermost energy level. And that's going to be the same thing that's true for all of these guys going all the way down. Hydrogen, lithium, sodium, potassium, rubidium, everything in this column has 1 electron in its outermost energy level, or 1 valence electron. When I get to the second column, when I get to beryllium, it's got 2 electrons in its outermost energy level, or 2 valence electrons. Magnesium is the same way, so is calcium, so is strontium, so is barium. So the number of valence electrons for your first 2 columns is this 1 and this 2, and then we're going to jump over here. Now these guys here in the middle, they're called transitionals. They're a little bit different, they act different, they behave different, and so when we talk about valence electrons, they're not going to follow the same type of rules that we think of when we see these. When we get from beryllium to boron, boron has 3 valence electrons. I went, because this was 1, this was 2, so this is going to be 3. This is going to be 4, 5, 6, 7, and 8. So if you want to know how many valence electrons are in a column, look at this number right here. Whatever number is in the units place of your number. So there's 3 valence electrons, there's 4, there's 5, there's 6, there's 7, and there's 8. That's just a little mnemonic for remembering how many valence electrons there are in each column. And so in the world of atoms, this column here, column number 18, or family or group 18, these guys are called noble gases. So family number 18 are the noble gases. And what's true about the noble gases is that their outer energy level of electrons is full. They have the maximum number of valence electrons that can fit within that energy level. And so, so for them, the outer energy level is full. And I'm going to mention this real briefly because we're going to talk a whole lot about it in our next lesson. But everybody wants to look like a noble gas. The noble gases, they're like nobility. They're noble. And so just like if you have a king or a queen or a prince, everybody wants to be noble. Everybody wants to be important. And so in the world of the elements, everybody wants to be like a noble gas. And we'll talk more in the next video about how that actually plays out. Okay, so that is our families or groups. So everybody here has 8 valence electrons. If you look at column number 15, family 15 or group 15, how many valence electrons do they have? Do you remember how I just told you to tell? Yeah, column number 15, group 15 that just has nitrogen on the top. Everybody there has 5 valence electrons. How about group 2? How many do they have? You should have said 2 valence electrons, okay? How about group number 13? How many valence electrons do they have? Yeah, 13, they have 3 valence electrons in their outermost shell. And so everybody all the way down has the same number of valence electrons, okay? So those are our columns. Now, the other thing we want to talk about is the rows going across, and those are called periods. So the periods go across, and for those, the row number is equal to the number of energy levels that the electrons are going to occupy. Okay, so you can see over here, it goes all the way up to 7. 1, 2, 3, 4, 5, 6, 7. And so I have 7 energy levels represented by the elements, or that the elements on the periodic table will have. So I can get up to 7 layers on my onion. Okay. Now, what about these 2 groups down here? In your book, you can see that they actually have a couple of lines that go from here to here and from here down to here. And if you look at the atomic numbers on there, you can see that what is actually the case is that lanthanum, which is right here, is element number 57, and then cesium down here is element number 58. And so what really would need to happen is that we would have to like cut the periodic table right here and slide it apart, and then take this one and slide it up in the hole, okay? The reason that we put them down here is just because we'd have a hard time printing this periodic table on one sheet of paper because it would be way too long. So we just do this for convenience's sake, as far as getting the periodic table into a horizontal measurement that is going to make it possible for us to get it printed and to get it displayed in a reasonable fashion. So in actuality, what you're going to see then is that this is actually part of period 6, and this row down here is actually a part of period 7. So we really only have 7 periods on the periodic table. Okay, so let's do a couple of examples now. Let's say that I have lithium, and I want to know what period and what group these atoms are. So we're just practicing here. So where is lithium on the periodic table, the Li? Well, lithium is right there. So what period is that in? And remember, period is what goes across. And the way you can remember that is that when you write a sentence, you go from left to right and you put a period at the end. So since sentences in the English language go horizontally, and you put a period at the end, the period is also going to go horizontally on the periodic table. So what period is lithium in? Well, it's in the 2nd row, so that means it's in period 2. What group is it in? Well, lithium is in the 1st column, so it's in group number 1. Okay, how about silicon? Silicon dioxide is what makes up sand. So silicon, when you combine it with oxygen, will make sand. So where's silicon on the periodic table? This may look like a huge jumble of letters to you right now. The ones that we use a lot, you'll pretty quickly learn where they are. And most of the elements that we use or that I give you, they're going to be in this top portion of the periodic table. I'm not going to give you a lot that are down here, unless maybe they're over on the edges. Okay, so silicon is right here. You see it on your periodic table? What period and what group are silicon in? Well, silicon is in the 3rd row, so that means it's in period 3. Silicon is in the 14th column, so that means it's group 14. How many valence electrons does silicon have? If you said 4, you're right. It's got 4 valence electrons because of this 4 right here. How many valence electrons does lithium have? If you said 1, you're correct. 1 valence electron because it's in group 1. Do a couple of more. How about calcium? Calcium on the periodic table is over here. What period is calcium in? Remember, periods go across, just like sentences go across in the periods at the end. So calcium is in period 4. What group is it in? Well, the group is the column, and that's in group 2. How many valence electrons does it have? If you said 2 valence electrons, you are correct because it is in group 2. We'll try one more. Let's try iodine. Now, iodine is a little bit further down on the periodic table, so if I give you an element and you don't see it right away, if you kind of scan the top 2 or 3 rows, then kind of go down these 2 columns and go down these columns right here, because that's more than likely where you're going to find it. Okay, iodine is right here on the periodic table. What period is it in? Yep, period 5, because it's in the 5th row. And what group is iodine in? If you said 17, you are correct. Now, how many valence electrons does iodine have? Well, hopefully you said 7, because that's what's in the units place in the 17, so it has 7 valence electrons. Now, you are going to get a chance to practice this yourself today.